for two-dimensional systems, there's a nice compact way to describe the dynamics that can occur in 2 dimensions in terms of the determinant and the trace of the linear matrix. So let's sketch that. So if we have the linear matrix L, then we know about the eigenvalues that the trace of L is the sum of the 2 eigenvalues. First, the determinant of L is the product of the 2 eigenvalues. And therefore, you can simply write the eigenvalues in terms of the trace and the determinant when you get that it's the trace plus minus the trace squared minus 4 times the determinant of L divided by 2. So what are the relevant parameters? So what are the relevant aspects that we want to discriminate? So what we want to know is whether the fixed point is stable or unstable. And we want to know whether the instability or the dynamics are oscillatory or not oscillatory. And so we see that we can characterize that simply in terms of the trace and the determinant in the following way. So we have a change in stability that can occur in one of 2 ways. If we're looking for a complex pair crossing the imaginary axis, then we need to have the determinant, the square root, be imaginary, and the trace needs to be 0. Well, that means if the trace is 0, then the determinant has to be positive for that instability. Okay, so that is if the trace of L is equal to 0 and the determinant is positive, then we get an oscillatory instability, and lambda 1 and 2 are complex. And they change, the real part changes sign when the trace of L changes sign. Real eigenvalues occur in the following way. I mean, a real eigenvalue is going through 0. It goes to 0 when the trace is negative, and the square root compensates for that. So that would be the positive sign. And when the trace is negative and the determinant is 0, then the positive sign would lead to a 0 eigenvalue. So if the trace of L is 0, is negative, but the determinant of L is 0, then we have a steady bifurcation, a real eigenvalue. I shouldn't call it bifurcation yet. We just know about instabilities, right? So we just know we have a steady instability. Okay, the other thing we want to know is whether the eigenvalues are complex or real. And that, of course, is determined by the square root. And so we see that change occurs when the trace squared is equal to 4 times the determinant. So a change in character so there we have, if the trace L squared is equal to 4 times the determinant of L, that's when this happens. And let's be more concrete, we get complex eigenvalues. That's when this has to be negative, meaning the determinant has to be bigger than that. So if the determinant is bigger than the trace squared. Okay, so we can put that all together in a nice diagram where we simply just plot the determinant on one axis and the trace on the other axis. And then let's just note those different lines. So stability changes when the trace is 0 and the determinant is positive. That is here, right? So this is when we have an oscillatory instability. And more specifically, we have when the trace is positive, then both of these eigenvalues have positive real parts. And that means we have an unstable spiral. So we have an unstable spiral when the trace is positive, and when it's negative, we have a stable spiral. So we can actually draw that. Let's draw them. So here we have an unstable spiral. And here we have a stable spiral. Okay, the other stability limit is when the determinant is 0 and the trace is negative. That's down here. And what happens there? When the determinant is 0, then these two compensate, but that means the minus sign gives us actually a negative eigenvalue. So there's one eigenvalue, negative, independent of the sign of the determinant, and the other eigenvalue changes sign. So we go from 2 negative eigenvalues to 1 negative and 1 positive eigenvalue. And then finally, we have this line here where the character of the instability changes. And that's when the trace is squared is 4 times the determinant. That's a kind of parabolic shape. Looks like this. And on this line, we have both eigenvalues equal. So we have λ1 equals λ2 with degenerate eigenvalue. So that's when the character changes from spiral to not oscillating. And so that's this degenerate eigenvalue I said before, where we have one proper eigenvector and one generalized eigenvector. And so when we are then above here, we still have 2 positive eigenvalues, but now they're both real. And so we have actually an unstable node. Whereas here we have a stable node. And along the y-axis, the stable node turns into a saddle because one of the eigenvalues goes from negative to positive. And so we have here positive, negative. Let's mark that in addition. We also have here positive, negative. And then as we cross this line, they become both positive. So here we also have a saddle. Oh, let me do it the other way around. And so we have now an overview of all the possible instabilities that fixed point can have in 2 dimensions. And it's so we have spirals, unstable nodes, saddles, stable nodes, and spirals again.